You can start recording. Okay, hi everyone. Thank you so much for coming today. Today, I'm really excited to introduce something to you that has to do with numbers, but number patterns. And I'm sure you've also heard of it before. If not, then today's your introduction. Pascal's triangle. And it has like a bunch. So this is Pascal's triangle. It has like a bunch of different ways numbers interact with each other. What is Pascal's triangle? Pascal's triangle is this. But essentially what happens here is that you do so imagine there's little zeros here. Oh, this doesn't write. That's fine. Imagine there's zeros on either side, and basically what you do is you do 0 plus 1 to get the next number, which is 1, and then 0 plus 1 to get 1. And then you keep on doing that for every row. So in this case, you go like 0 plus 1 is 1, and then you go 1 plus 1 is 2, and then 1 plus 0 is 1. And that's how you continue down the pattern. Now this is also Pascal's triangle, but it introduces a new concept, which is combinatorics. Combinatorics is like the math of counting, essentially. So the biggest way you do it is the notation is like this. So the top, the ones in purple, is like, imagine if you're a group of people, that's how many people are in a group. So for example, for this one, if you have a group of 0 and you're finding all the combinations where you pick 0 people, the little red ones are how many basically spots you need to fill. And so those are like the lengths of the subsets. So essentially let's do a different one. So let's say you have 2 people and you're finding all the combinations to pick 0 people. There would only be one combination because you just don't pick any people. For this one, when you have 2 people and you need to pick one person, person A, the first person will be called, and that's one subset. And then another subset would be when the second person is called. And that leads to 2 combinations. And then that's kind of how it is. So yeah, that's the combinatorics Pascal's triangle. What I'm going to be proving today is something called the hockey stick identity, which is, it makes this first before I start, there's also different ones. So there's the Fibonacci sequence is 1, if you know what the Fibonacci sequence is, 1, 1, and you add the previous ones. So you do shallow lines, so it's 1, and then it's it's kind of hard to see here, but 1, 2, and then you go 1, 2, and then 2, 3. I should have put an image, but it's fine. But another cool thing with the pattern is that you start with 1, and each row is a double of the previous row. So it's if you add all the numbers in that row, so 1 is 1, and then 1 plus 1 is 2. 1 times 2 is 2, so that's a double. And then the next row, row 3, is 4, and then the next row is 8, and then you continue on. They're kind of like a double of each other. And this kind of happens because we see that each number is getting added twice, in a sense, to the next row. So let's take a look at this row. So this is 0 plus 1, it gets this 1. But then we add 1 plus 2 to get 3. So this one is basically being added to this position and this position, so it's doubling it. And so you do that for every one. So 1 plus 2 is the 3, and then we do 2 plus 1 is also the 3. So the 2 was added here and it was added here. So each number is being added twice to the next number, which is why it's like a double. Each row doubles in size when you add all the numbers up. Okay. So this is what the hockey stick identity looks like, and I'm going to start with a specific case so you can see it. So basically, it's a little hockey stick. So you go down as many as you possibly want. So you could go here, you can go here, as long as you follow this little shape. What it's saying is if you add each one of these, you should get this number. So if we go back to the other one, right, we're looking at 1 plus 3 plus 6 plus 10 is equal to 20. And that is correct, but why does this work? And why does that work for any part on the triangle? 1 plus 2 is 3, 1 plus 3 is 4. So why does that work for every single part of the triangle? Well, we'll start with a specific set. So let's say you have set S. So this is the example I'm doing. So let me write it here. So we're trying to prove that 2, 3, 2, 4, 2. say each of these is 2, pick 2, and then, or 2, choose 2, 3, choose 2, 4, choose 2, 5, choose 2, and then 6, choose 3. So that's essentially what I'm doing with this. So to make it easier, instead of doing numbers or whatever, I'm going to do a set of ABC. So 6 letters, A, B, C, D, E, F. And let's say those are all the people in our group, right? There's 6 people, and we're basically finding all the subsets, all the number of different combinations when we pick 3 people. So the best way to think about this is kind of brute forcing it, and how you brute force it is to start with all the subsets that start with A. And so there's going to be 10 subsets that start with A. ABC, ABD, ABE, all the way down to B's. And I kind of already did this work because it would be tedious to write them all out. But these are all the subsets when A is in the first position, or position 0. So A is always in the first position for these. So we have all the subsets with A, right? And that's 10. Now we're going to move on to subsets with B. So again, kind of how we're thinking, right? We only have 3 positions, right? Because we're picking 3 to fill out of 6 people. So, but now we're getting rid of A. We don't need A anymore. We already have the subsets. So we're now focusing on B. So these are all the subsets with B. And that is 6. There's 6 subsets with B. Okay, now we got rid of all the subsets with A and B. Now we got to move down to C. And C, these are the 3 for C, when C is in the first position, and then D. And the reason why we don't have any subsets that start with E or F is because when you look at all these, F is in there in all the subsets. Essentially what we're doing by going alphabetically is that we can't have a subset with only 2, right? Because we're specifically asking when we're picking 3. So there needs to be 3 spots to fill. So since we went alphabetical, there's nothing that's going to start with E or F that's not already up there. And in this case, position does matter. Yes, position does matter, meaning that if you rearrange them, it's still the same. So if we did ABC, right, that's a subset. BAC is the exact same thing. Even though the order's messed up, it doesn't matter. It's still the same exact combination of ones, basically. So that's why that works. And now if you observe that, we see like there's 10 here, there's 6 here, there's 3 here, and there's 1 there. That's very familiar, right? We have 1 plus 3 plus 6 plus 10, which happens to equal 1. So we know it works for this case, right? Because we can go back and look at it here, right? So I did that with the numbers brute forcing. Now let's do it in the combinatorics way, right? So we already know this is the same, right? We have 2 people and we need to pick 2 people. There's only 1 combination. So that checks out. We have 3 people and we need to pick 2 people. How many combinations are there? Well, if you think about it, we have 3 people, A, B, C, and we need to pick 2 of them. We could start with all the ones that start with A. It would be A, B, and then A, C. Now we could do the ones that start with B, B, C. So that's 3. Now for 4, it's the same thing. We have A, B, C, D, and we need to pick 2. So we can do A, B, A, C, and A, D. That's 3 there. And then we already finished A, so we can do now start with B, B, C, B, D, and then the last one, and that's 6. So this one would be more work, but essentially you get the point, right? This is how you brute force it and double checking it. So this is just another way of writing this notation. It's just all the combinations. So 3 choose 2, 4 choose 2, 5 choose 2 is, and that goes on up, is equal to 6 choose 3. Now the general proof is a little bit more complicated than that, but we know it works. So we know it works. We have a specific case that shows why it works, but why does it work for every case? It works for every case because of the method we use by group forcing. So essentially, you have a group of n+1 people. That could be any amount. It could be essentially infinite, it doesn't matter. And we're choosing k+1 people. So first think of it like that. This is also the 6 choose 3, if you want to go back to that. That's another way of writing 6 choose 3 for this. Now we have the 5 choose 2, the 4 choose 2, 3 choose 2, and 2 choose 2. Basically, another way to write these, if you notice, 3 is one more than all the numbers that we're filling here. So like 5 choose 2, that is, the 2 is 1 less than the 3. So we can write this as, and then 5 is 1 less than the 6. So we can write this as n choose k. And then we can keep on going for an infinite amount of little like things we have. So we can just continue that. We could go n minus 1, and then k stays, right? Because these are all the same here. We can keep going. And essentially we end up with every group we go at is going to have the number that's going to be the same. So it's going to be k, right? Because we can't have k minus 1 people and choose k people. That's not possible. Like 3 choose 6 is not a thing. You can't have 3 people and choose 6 people. So that's why that's going to be our last one. Okay, and if we could write this in like a summation, so I'll do that real fast. So n+1, choose k+1 people. And essentially we're summing from I equals k to n. If you don't know how a summation works, basically each round if you go through I increases by 1. So what we can do here is we could put k at the bottom and then we could put I on top. So we'll start with this one, right? Because I equals k the first time around. And so it'll start with k and then it'll go all the way up to n. So this includes all numbers that you could possibly choose. So you can go as big or as small as you want, and this will always work. This form will always work. Now, that's kind of what I've written up here. But that's good, but another way to think about it is if you have, take, for example, this classroom. If we were to order everyone in alphabetical order in a line, we can start with, let's say the first person's Ali. Ali will be first in the line, and we'll go all the way through how many people there are. Infinite people, 5 people, it doesn't matter. And we'll start with the person who's alphabetically the highest, in a sense, and so they'll be in position 0, and everyone's waiting right after them. So what you're gonna do is the same thing that we did with the A, B, C, D, E, F, and you're gonna call Ali first. And essentially what we're doing by calling Ali first, we're looking at this group, right? So we remove Ali from the n+1 group, right? n+1 group, we remove Ali first, okay? So now who do we have left? She's guaranteed the first position, and so we have still 2 other spots to fill, or however many spots to fill. We still have k spots to fill, because by also putting Ali first, she also takes up the first spot. So we're doing k+1 minus Ali, which is k. And then so that's how we get this group. So these are basically all the groups with Ali, because when she's in the first position and she's removed from the total number of people, we have n people to choose from now and k spots to fill. Okay, so when you do all the subsets with Ali or whoever's in the first position, and now you can move on to the next person. So let's say Bill is in the next line. So Ali can be disregarded to the side for now because all her subsets are done. So Bill's next in line, and well, Bill goes first. So we still have 3 spots to fill, or however many spots to fill. And now we're looking at Bill and all his subsets. So why does this happen? Well, if you think about it when Bill's in the first position, we still have to still fill up the k remaining spots. right? We're not essentially making the spots smaller. We're not only doing 2 people, we have to go up to like however many spots we need to fill. So Bill's there in the first position, but now we have to remove both Bill and Allie, because now we can't include Allie anymore, as we discussed. ABC is the same as BCA. So Allie's no longer allowed to be in the subsets. So we have to remove both Allie and Bill from the number of people to pick. So our group is getting smaller, and however many people, we keep on going. So let's say Kathy is next in line. Kathy's next in line, but we got rid of Bill and Allie, their subsets are done. So now Kathy moves forward, she's in the first position. We still have those remaining spots to fill, which is K. That stays the same. But now we have to remove Kathy. So we do N plus 1, but we remove Allie, Bill, and now Kathy. And we fill all her subspots. We do all her subsets. And essentially you can do that throughout the whole group. And you'll be left with the last person. Let's say it's Xavier. Xavier is the last person. Well, we can't go up to Xavier because if he's the last person, he can't be the only person in the subgroup, unless we're looking at a size of 1. But so basically, the last person is going to be that equals K. And this K is important because if we have, go back to our example of 3, right? The last 3 letters, which D, E, F, right? We can't go past D because we have to think the group, the entire group. So although Xavier's last, he's going to be part of the other 2 people that are in front of him. So let's say the third to last person in this sense is Will. Will's the third to last person, and so he's going to take, Will's there, and there's only K people left. There's only K people left, so they have to move forward. They have to be a part of this subset. And that essentially breaks the cycle, because if we're done with Will and we move on to the next person, there's not going to be enough people to fill the spots. And yeah, that's pretty much it. That's the hockey stick identity. And yeah, thank you.